Test, test, test. So, thank you all. We're going to begin the second session now. And so this morning we saw with Professor Bimbo the challenge of maintaining compatibility whenever a model undergoes updates. When it was talking about the large models updating. And so for the beginning of this afternoon, we have the honor to receive Mr. Mubarak Shah, which is coming from the University of Central Florida, and you're going to talk about the diffusion models in computer vision, And the question will be the following one: how diffusion models can be employed for solving computer vision problems. Professor Mubarak Shah, it's your turn. Thank you.
Is it on? Is it on? Okay. Okay. Okay, yeah, thank you very much. I'm pleased to be here. This is the first time in Morocco. I've been really enjoying. So I'm going to talk about the diffusion models in computer vision. So the diffusion models are generative models, and they involve the reversing the process of gradually degrading data. Okay, data in this case can be images. So they consist of two processes. One is called forward process. So we have, say, distribution of our data, particular data set. So we'll take a sample from there and we'll keep adding noise until it becomes complete noise. Okay, so it will be a point in the normal distribution, Gaussian distribution, and that's called forward process. Now, there's a reverse process where we will sample a point from the Gaussian distribution. We will denoise it, keep denoising until it becomes one of the sample. So that's a very high-level overview of diffusion model. Now, the example here is you have image x0, and you keep adding noise from x0 to x1, x2, x3, and so on, xn. Now, xn is complete noise. It doesn't have anything with the image. Now, we then sample from that distribution and keep denoising. That's a backward process. And at the end, it will become a sample from the distribution. So that's called diffusion model. Okay? So what is the part which is relates to learning? So what we do is we learn this UNet architecture. So UNet has encoder and decoder. So we put a noisy image and we want to estimate what is the noise in that, okay? So this is like a mean of the Gaussian distribution for which this image has a noise. And that will give us the denoise image, or it will, give us some parameters of this distribution, and that will be, we will take then denoise image, we'll bring it back, and we will get another denoise image, keep going that, and at the end we will get a sample from the distribution. So the learning part is given the noise image, how do we remove the noise, or how do we estimate the distribution of the noise. So that's the process, okay? Now, this is one of the most active area of research in machine learning and computer vision. And actually started, the first paper was 2015, and there was nothing for several years. Then started something 2019. Now it is really, really hot area. And these are the number of papers in the top conferences in last year, and these are the papers so far in the March this year. So as you see, it's really going very rapidly. So we had a very nice survey paper in IEEE PME with my collaborators from the University of Bucharest, and we also have a GitHub page where we actually collect all the papers in this area. So if anybody's interested in, you can look at that. So in this talk, I'm quickly going going to talk about 5 different things. So first one is the person image synthesis. So we are given source image and the pose of that person, and we want to generate a new image which is like this. As you see, this guy was facing towards you. Now we want to change it and face it like this. This is a synthetic image and look real. So then I'll talk about how the diffusion model can be applied to solve the computer vision problems. So one problem in computer vision is person re-identification. You see a person in one camera, that person reappears in second camera, can we recognize the same person? So now the problem has become more difficult when the person can change the clothes. So we are going to talk about how we can generate extra samples to actually train the model which works better. Then I will talk about another problem in computer vision, which is called geolocalization. Given an image, we want to find out where the picture was taken. What's the GPS location of that? And we'll show you that how the diffusion model can help us. Then I'll talk about the video action segmentation. So we are given a video like this, and we want to classify each frame that what action is being performed. And then I will end the presentation talking about how we can involve the equivalent representation constraint diffusion model to improve the image synthesis, which will be better than if you don't use that. Okay? So let's go through the first part. So this was the paper in CVPR last year. And so the problem here is that we want to show that how the denoising diffusion model can be applied to create very realistic looking high fidelity person images. So the problem is we are given a source image, XS, and we are going to pose that how the person, the different parts of body are situated, and we want to generate this image. As you see, the pose changes, but this is a synthetic image, but it looks very real. So the approach is that we are going to use the interplay between the appearance, the person looks real, and also the pose is correct. So for that, we need to disentangle this information, the pose and the image, and we are going to use the what is called classifier free guidance. So source image appearance and also target pose in this case. So again, this is our source image and this is a pose, and we will have the sample from a noise, Gaussian distribution, and we will do different diffusion steps, and at the end noise will remove, we'll get the image like that. So this is a conditional because it's conditioned on the source image and also the pose, okay? So we will get the image like this. So now the little bit more detail. So we will have the unit, which is the noise prediction module, as I explained earlier. And we will have the source image, and then we will encode the source image. We'll have another encoder, which we call text encoder, and we will then inject that in the original unit, as shown here, to make sure that the image we generate is for that particular source image. Okay? And then at the end, we will estimate the noise, which is conditioned on the source image, the pose, the time, of course, and the sample from the Gaussian distribution at time t. So a little bit more detail. So we have these two, and we are going to, the way we are going to include the source image, we will do this kind of cross attention. And we will have this texture diffusion block, and we will take this cross attention between the source image and the actual, this unit output encoder from the noise, and this will become query, and then we'll have key and value coming from the encoder of the source image. So, so that's the idea. Now, if you do all that, we will get something like from the Gaussian distribution, source image and pose, and we will come up with the image which will look like this. So now when we compare this output using this method, it looks like that, which is reasonable, but it's not, as good as the ground truth. It should look like that. As you see, the shirt colors have changed. It's not as good. So how do we improve that? So what we are going to do is we are going to use the classifier free guidance. Okay. So the basic idea is that when we are using the vanilla sampling, we have the YT, the sample from Gaussian distribution, the pose, and the source image, and we were putting this in the unit, and we were estimating noise. But now what we are going to do, classifier guidance, free guidance, we will have, one will be unconditional generation, which means we won't have any of the source here. We will just sample from the distribution, and we will generate for that particular YT, we'll generate the noise and we'll denoise that. So that doesn't have any condition, unconditional. Then we will have the condition where we are going to put the XS, which is source image. So we kind of entangling these two information. And that will give us the noise estimated unconditional and noise estimated from conditional. We are going to subtract that, and we'll have this scale factor which will help us. And so we will have, when we do the unconditional, there's no pose, no source. And we do conditional, we'll have source and pose. And we are going to combine these two. And this is the actually better way to generate an image. And we can see that this image is closer to ground truth, but it's still, it is not, really what we want. So we're going to do one more thing. And we are going to do separation of the pose and the style. And that way, we can generate unconditional image. There's no condition at all. And we will generate the condition in the pose. And then we'll generate condition on the style. So we'll have these three terms. And that will actually give us the better results. And that's what we are going to use. So, and we're going to select these scale factors and so on. And this will be the results. So as you see that we do pretty well. These are different metrics for how good are your images, FID, SSIM, and so on. And this another data set, deep fashion, and this is the market data set. So now these are the results. As you can see that this is our pose, this is the input, and we want to generate the image of that person, which is different pose, and this is a ground truth. This is what we have, and these are the methods, and as you see, they have some problems. So this is another example. Again, this is a ground truth, and this is ours, and then we have lots of examples. And these are synthetic images, and they look very real, and that's the very impressive thing about diffusion model, that they can generate very realistic look at images. Okay, so summary that we have diffusion-based approach for pose-guided person image generation, and we have texture diffusion model, which is disentangling the classifier guidance, and we are going to model the correspondence between appearance and pose, and this we evaluated on extensive qualitative and quantitative comparison, and it gives us pretty good results compared to state of art. So this is the first piece. So now we want to look at the second piece, and here we want to do the person re-identification. We want to re-identify a person. Now this problem is pretty popular, and we have been working on this for several years in this area. So the idea is that we want to retrieve a person of interest across multiple non-overlapping cameras, okay? So here's an example. So we have a database like this, and we have a query image. We want to find out that this person matches which person in our database. And these are the green one matches, and the red one doesn't match, okay? So we want to retrieve that rank list. This is the best match, this is the second best match, and so on. So this is the standard person re-identification. And we apply the previous method because we can synthesize new images using our synthesis method using diffusion model I described. And that helps, that can improve the results compared to other methods. As you see, these are the results from the previous method I just explained to you, PIDM. But now we want to actually solve more difficult problem. We want to solve the problem where we can recognize even the person is changing clothes, okay? So this is the same person, but looks very different even for humans, right? This is another, famous person, and this is another famous singer. Now, she looks very, very different in different clothes, and it's difficult even for humans to recognize that. So the cloth changing re-ID is a newer problem. So here is an example that this person, the cloths are consistent, as you see here. This different viewpoint, different camera, but the same person. But here is completely different because the clothes have changed. So we want to match this person with these. And it's a much more challenging job as compared to matching this person with these, which is the harder part, okay? So now we want to solve this problem, and we want to use the diffusion model to do that. We will generate additional samples for training the re-ID model using diffusion model, okay? So now what we will be able to do is that we take the original image, and there can be simple method to synthesize different images of the same person. Suppose we can change a color. And if you apply the standard diffusion model, it looks like this person can look like this. But what we are going to do, we will generate this kind of image, which is much better than these two images. And we will use those for training our model. So another example, suppose this original image. These can be, possible images to use, but they don't look realistic, okay? So we will be able to generate an image like this, and we're going to talk about that. So our approach is that we will extract the textual clothing description of the person, and we are going to use this visual language model, VLM, and also large language model. Okay, so then we will extract ID preserving mask for inpainting, and then we synthesize images to artificially change the clothing of a person. Okay, and it has to look realistic. Then we are going to train the cloth changing person identification model with these new images, and we will show that it can improve the performance. And we will have few other things. We'll do progressive learning, and we will also do the test time prediction, and I'm going to quickly go through that. Okay, so here is the whole method, but I'm going to go through different pieces. So first part is that we are given the person, and we are going to do segmentation to get a mask of this, okay? And then we are going to come up with what are the clothes this person is wearing, and we are going to apply a method called LAVA, which is the visual language model. Given an image will tells us, what the clothes person is wearing, and we will get different list of these clothes. Suppose here, as you see, the person is wearing striped black and white t-shirt, black and so on. This is another description. So we'll get a lot of description from the training data. And then we will use the large language model like ChatGPT to summarize those, because there may be some repeats and so on. And these will be the prompts we are going to use the text-to-image diffusion model to generate more images. Okay, so that's the basic idea. So that's what I just described. And then we have the standard diffusion model that we will take the sample from noise, and we are going to, first we will noise, take an image, we keep adding noise, becomes the Gaussian distribution, and when we do the backward process, we'll sample from here, and we'll get the actual sample from the noise, we'll convert it in the image. And these are the different training steps. So, so a little bit more detail. So we have original image, and we will get the predicted mask using segmentation method, and then we are going to take this to the stable diffusion. It's a pre-trained model. We are going to just use that, and we will get a prompt, say black and white striped t-shirt, black pants and black shoes. So this person will be changed to this person, which is generated image, which is different than this one. And that's what we want to do. That looks real, but different clothes. And that will give us the more samples. Okay? So, so now this is explained a little more. So how we are going to actually train this. So we will have this sample from the 2 clothes ID, this is sample from 3 clothes ID, and so on. And this will go to here, where we are going to take these original training batch, and we will combine with the synthetic images we generated, and we'll go to the person ID model. And that's it. That's basically what we are going to do. Now we will do one more thing. We'll refine the prediction. Instead of giving one query image, we are going to actually take that query image and synthesize 5 different images of that with different clothes. So maybe there's a match for that particular person, different clothes in the database, and that actually helps us. So we'll compute the features and get the features of the additional 5 images, and we combine those, and we retrieve the matches, and we will kind of average all those to actually improve the retrieval method. So, so here's an example. So this is the original image, and these are the generated images. As you see, that's the same person, but wearing different clothes. This is another example, and this is 400 meters from the camera, so these images are not that clear, but still I think we can generate nice looking images. And this is even 500 meters, so that also works pretty well. So these are the kind of more examples that now this is the original image, and we give a prompt, white shirt, blue jeans, and white shoes. And this is the image. And we actually have to hide the ID, because this is a program, government doesn't want us to show the face, but it looks very real, right? So this is from here to here. And this is a striped top, white short, white shoes, like that. So there are some more examples which are shown here. Okay? So, and some more examples, as you see here, completely different. This is the original image, and it's a blue jeans, black and white shoes, pink shirt. Looks like this. Here's a white shirt, khaki pants, and white shoes. and so on. So these are the results compared to other methods. We can get a pretty good improvement at 8.6 to 4.7 in MAP. And this is the cloth changing ID, and we can get improvement 3.7, 3.2. And this is another data set. Again, we have good results, and this is a hardest data set. Again, we can make a difference here. And now, not only we can use our method with these test time augmentation and all those things I talked about, but we can just use other method but generate new data using our method, and we try that also, okay? So this is another method, but we generate more data, we can actually make about 11% or 12% difference in MAP. And this is another method, about 28%, and so on. So this actually helps to generate more data to actually improve the cloth changing re-ID, because these extra sample really help a lot. So these are this is project funded by IARPA Breyer. So they have a different matrix, which is the true positive rate. And before that, we had these results, but we can improve about 5% and so on. This is another matrix they had, and this is actually harder open set where we don't know those people and so on. So we did the ablation, like different components I talk about, that we are getting we are applying the LLMs and VLMs to get the whole possible clothes. So this is, we have another part of this diffusion model where we add a discriminator part, which is similar to gain, and progressive learning that we slowly introduce these synthetic data and prediction refinement. As I said, given the query, we generate 5 different examples of that query with different clothes, and that also helps. So these are different things that if we don't do anything, then we get about 55. And when we just use only standard diffusion model, like a stable diffusion, it helps a little bit, but not that much. But when we start using our methods, and it helps, and which is shown here, that using the LLM and VLM, we can get a nice list of the clothes, and we can improve that, and this helps when we introduce discriminator and so on. And this is progressive learning. Don't introduce all these synthetic, but slowly introduce synthetic with the real, and there's final one where prediction refinement. So we get about 11% improvement, which is good. Okay, in summary for this, that we have used the diffusion model to solve the cloth changing re-ID problem, which is a very challenging problem. And we use these prompts which were extracted from the large language model and visual language model. And that is kind of really impact on the research. Instead of asking people to look at these images, come up with a list of clothes wearing, it's a lot of time consuming, but we give the image to the visual language model it gives you. Now we have a lot of list of those. Then to summarize, we can manually summarize, because there are a lot of duplicates and so on, but we give it to ChatGPT and it summarizes. So that's why, how these visual language model and large language model impacting the research in computer vision. And we'll talk about that more in the panel session tomorrow. So progressive learning strategy help, because if you introduce the real with the synthetic all together, then we found out it's not really helping much. But if we introduce progressively just one sample from the real, one sample from the synthetic, and next time one sample from real, two samples from the synthetic, and so on. Gradually, it's learning better as compared to just using in one shot. And also test time augmentation also helps. Okay? So that's the second piece. So let's go to now third piece. And here we are interested in problem what is called where am I? So suppose you are somewhere, you are lost and your cell phone doesn't work and you don't know where you are. So suppose this is, and you have a camera, you take a picture, and we have a method which will tell you your GPS location. And somehow this picture was taken in Pittsburgh, and this is the GPS location of that, okay? And this is pretty useful in self-driving car where GPS doesn't work. Then this kind of visual localization is pretty useful. So the idea is that you are given a query image and you have reference images. For each of reference image, you have the GPS location stored. So you essentially take the query image, match with all the reference images, which is the closest one, you just transfer the GPS location of that. That's the retrieval problem as Alberto talked about earlier this morning. So now the question is that our reference, our query image is a street view, on the ground. And the reference image is the aerial view from the top. And there is a big gap, and we want to be able to match this image with that. It's a very difficult problem, okay? So now the reference and the query image can be panorama, 360 degrees, like a Google Street View. But it can be only just half of it, 180 degrees. Or it can be only just quarter, 90 degrees. So this will be the easier, but when you go here, it will be much harder. So actually these are the existing methods. When you have 360 degrees, the performance is pretty good, which is shown in red. But when you have only 90 degrees, performance goes down. So this is called limited field of view. You only have part of it. And so we want to solve this problem. And we want to use diffusion model to help us. Okay? So we want to come up with a method to improve the limited field of view cross-view geolocalization. Cross-view means ground to air, ground to top. And so we have these two-stage approaches, two-stage approach. First is, again, we are going to synthesize new images, okay? And that's where we are going to use the diffusion model. And once we have that, then we will have feature aggregation to use the retrieval method, okay? So, so this is the overall picture. So let's go through each separately. So let's say we are given an aerial image. So we can apply a polar transformation to get corresponding approximation of the ground image, okay? And so we will have this module which will have this image and also the limited field of view image. And we want to come up with the full panorama given this image, okay? So that's what we want to use the diffusion model for. Now once we have that, then the retrieval will become easier because we are given the query image and we will retrieve the top K aerial images, and which may look like this. Now we will take these aerial image and the query image, which is street view, and we are going to generate a full panorama because these query images only limited field of view, only 90 degrees. It doesn't show the whole thing. So that's what we are going to learn. Stage one, given this and given this, we are going to come up with that, using diffusion model. And once we have that, then we will take these images, and we will use any cross-view image geolocalization. We'll get the features of those, and then we'll match those to query and do kind of nearest neighbor in our database, and we'll retrieve that best match, and that will be a GPS location of this image. So that's kind of general idea. Okay? So the most important thing is this part where we are going to actually synthesize the full 360-degree view image given the limited field of view. So here is a starting point. So we take the aerial image, and then we generate this using the polar transformation, but this doesn't look like that accurate as compared to the real the street view image. Okay, so we want to improve that, and does not depend on the limited field of view street view image, because this is just obtained from the aerial. So we want to be able to, given the particular limited field of view street view, we want to generate a full image like this. And so we want to condition it not only polar image, but also limited field of view street view image also. So this is going to work that we are going to use sequential masking and replacing based diffusion strategy. And so since we don't have a full panorama, so we are going to actually pad some zeros to get the full 360 degrees, because at the end we want to get the full panorama. And then we'll feed it to the train diffusion model, and then we'll do the forward process, and then from there we'll do the backward process. Okay? So here is the more pictorial explanation. So this is where we start. Limited field of view 90 degrees. And now we generate this full 360-degree panorama. We just put part of it, and other one we will just put the zeros, okay, to start with. So then we will have this mask M. Here are the ones, because that's what we have, and here are the zeros. So now we'll do the forward process. We will have this forward process street view, zero iteration, then we will add noise, and we will add some condition, and it will look like this. We'll take this one and do the next iteration. We'll keep adding noise and noise. That's what diffusion model does, the forward process, as I explained earlier. So then we reach at the Tth iteration, then it's complete noise. Okay? So then we'll do now the backward process. We'll sample from the Gaussian distribution, and then we will denoise. Now, when we denoise, we are going to keep in mind that we started only this part, because we only have this 90 degrees field of view. We put it zeros there. So this is our mask, and we are going to use that fact. And we will have another mask, complement of that, 1 minus m, and we're going to use those, both of those. So we will multiply with this, and now we will have this filled with zeros and this filled 1. Because we want to synthesize this one actually. We want to maintain what we have before. Okay? So this will continue t minus 1, and we will take the mask m and then multiply with that, and like this one, and then we are going to combine these two, part of it which is original and part of synthesized image, and that's it. So we'll keep repeating this, and we'll get the image what we want. So these are the results. So given this, we will be able to generate this. Okay? So this is synthesized, but it looks very real. This is the complete panorama given this one. And similarly, given this one, we can generate this one. Okay? And so on. So now first we want to say how well we generated these missing view completion, and we look at the FID and IS scores, and this lower the better, this higher the better, so we do pretty well compared to other methods. And now when we use this to solve the cross-view geolocalization with limited field of view, then we can improve our performance, as you see in all these cases, whether 90 degrees, 180 degrees, 270 degrees, and so on. It's one data set, another data set, and this is the actually most difficult data set, bigger, and we do pretty well also. So in summary, in this part, we propose a method we can improve the limited field of view cross-view geolocalization. Okay, it's a two-stage approach. So first approach, we want to synthesize new images, and for part of the panorama which is missing, we only have one part, we want to complete it. And second stage, we use that nice retrieval method. We retrieve the top K and we use those embedding, average, and so on. So again, you can see in all these retrieval is important. That's what Alberto talked about this morning. So this is the third part. Okay, so let's go to the next part. So far I'm talking about the images. Now we're going to talk about the video. So this was a paper in ICCV last year. So the problem is, given video like this, we want to be able to say what action is being performed in each of the frame. So this one is a ground truth, and this is the results we have. And each color represents different action. Okay? So that is the problem we want to solve. And so starting with complete noise, as you see in the top, is we start a complete noise. At the end, we want to come up with something like this, which is amazing, right? So it tells you that this is the action people perform in these frames, and then similarly, the second one and the third one, keep iterating, it come up with a very meaningful information, which is, very nice, powerful method using diffusion model. So in this one, again, the conditional generation. So we are going to generate these results for the segmentation, action segmentation based on condition. And it will be conditioned on video. Okay, so in this particular video, what action is being performed? So it's a diffusion-based snare framework, and we're going to iteratively refine. Starting with noise, we'll keep removing noise with a conditioned particular video, and we'll come up with what actions are being performed. Okay? So in this one, we are going to use some human action prior, which will help us to actually improve the results. And so here is the method. So we have a video. These are different frames of video, and we compute features of video. And that code encoder, transformer encoder, and we get the encoded features here. Okay? So then, for this video, we have a ground truth. We know for this video, this green is the action for this first part, then different action, orange, different action, blue. So we know that. So we are going to take this and we'll add noise to that. It'll become like this, we'll keep adding noise. Okay? So then, now we have a decoder. So decoder have input from the encoded features of video and also input from the noise ground truth. And the job of decoder is to come up with denoise sequence. And that will become the result. After many iterations, it will become the result that this is the action performed in different frames and so on. So let's talk about how we're going to train this thing. Because this is actually solving real problem. It's not just image synthesis. It's going to, given a video, it's going to tell you what action is being performed. So the loss function first is we will have a cross entropy, right? Because we know that what action is in ground truth and what action the network, the decoder is predicting, we want to minimize the cross entropy loss, okay? So the next one is that we want such that there is a temporal smoothness, which means the action at the I and I plus 1, the difference should not be that much, because there cannot be abrupt change. So that is the difference. That's another constraint, temporal smoothness. Then also we want to make sure the boundary of these actions are aligned with the boundary of ground truth. So this is the boundaries constraint. So we're going to use these losses to actually train our network. So, so now we have these, we are going to extract features from the video, as I say. We'll add the random noise. Then third is we're going to talk about how we can use the mask features. So in this one, we are not going to use the every time get the video and features, but we are going to do some masking, and that actually will help us. So that will encourage the model to reason our information other than visual features, because this is visual feature extracted from the encoder, from the video. So what those are, we want to introduce time, location, action duration, and temporal contents and so on. So one will be that we won't mask. Whatever the features are, we'll send it to decoder, okay? And other will be, we'll mask all the frames. So it'll be, there won't be no input from the video, but only whatever this has the noise features which are coming to decoder from the distribution which we learn, okay? So then we will have also, we'll mask the boundary frames. So we'll challenge the network that it can predict the correct boundary even though we have masked the features as boundaries, okay? So which is shown here. And then the last one will be, we'll randomly select some segments and we'll mask them. So the network does not have that information, and we'll challenge it to actually learn that. So that's it. So then I think it works pretty well. And so this is a comparison on the 3 different data sets. And these are different methods, different colors. And we can see that this is second method, as former, and so on. And this is third one and fourth one. And this is our method, which is shown blue. So it, performs, better in a couple of data sets and very close in the other one. So it's, achieved the comparable results with Gate A and better results on 50 sellouts in the breakfast data set. Then if you look at the different components of our method, like we talk about the cross entropy loss, boundary loss, and smooth loss, this is a different performance. And when we use all of them, then we get a better both performance. Each component is making a difference, which is good. And here is about priors we use. No masking, all masking, boundary masking, and selected masking, and that also shows that. So these are some qualitative results. As you see here, that we are playing this fast, so, to show, but as we're going through this thing, we can actually see it's pretty close to the ground truth. This is one, and then here we have the second example Um, and these are like kitchen things, so there are a lot of small actions being performed, and we want to separate those. This is another example. So here you will see the different names of the action. Pour milk, so it's pouring the milk, and then after that there'll be some other actions which will change. So it's a spoon powder, we're going to spoon powder here, and so on. Of course, it's not 100% exactly. It's a very difficult problem, but most of the time it works pretty well. Here's a mistake, and then at the end you will have the correct one, which is the step. Okay. So in summary, so we have the conditional generation formulation of action segmentation as an action sequence generation conditional video. And we use the diffusion-based framework as iterative refinement based on denoising diffusion process. And we use this prior and condition masking to further exploit the bias of human action. And this was an ICCV paper. Okay, so let's go through the last piece, then I'll be done and you can ask questions. So in this one, we are going to introduce what is called equivariant implementation in diffusion model to improve the performance. So now we know about invariance and equivariance. Okay, so let me just summarize that. So function f is invariant to group of actions phi such that change in image x by action phi does not change value of function. It's invariant. Apply transformation, but it doesn't change. Okay? So this is the idea. So we apply transformation phi to x. So f of phi x is same as f of x. Invariant, does not change. Okay? So here's the example. So we have image, and we send it to classifier, it said cat, and we translate, send it to classifier, it said still cat, invariant. Okay? So then equivariance. Function f is equivariant under group of action phi such that change in x by action phi changes function phi by equivalent transformation. So it actually changes, it's not invariant. So here's the example. So we apply the transformation to x, phi, then f of phi x should be f of x, apply the transformation phi. So this is different from here. Here does not change, but in order to get this one, then we have to apply phi transformation to f of x. That's called equivalent. So here's example. So we take an image, and let's say we want to take an image, find a silhouette of image, like here. Now we translate the image by this, and then we get a silhouette which looks like that. But in order this to be same, we have to apply transformation to this one, then it will be same. Otherwise it will not, because this looks different than this, because it's applied. So equivariant and invariant transformation. Okay? So we are going to show that if we apply this equivariant constraint, then it will improve the diffusion model. Okay. So here's a more demonstration. So we have an input space x, and we apply transformation to that. So this, suppose we translate the image look like that. Okay? And so we will have the deep network F, and another deep network F here. And so now we take image to this blue one, and this image to the black one, then this image to the orange one, and we want to relate that what is the equivalent transformation here. So now what's going to happen, that these features, which are shown here, and the features of the transformed image like this, if they are the same, then it's invariance, as I explained to you. So transformation x, f of that is same as f of x. Now, on the other hand, equivariance is different because these are the features of the transform version, which looks like this, very different. But in order to get this one same, then we have to apply transformation to that. And that's what we have done here. We apply transformation f of x, and it'll become like that. So that's equivariance constraint, which is important. So we want to import that to actually improve the diffusion model, and it's very important. So now what happened that since we talk about we are going to sample from noise, take a sample and denoise, it becomes sample, image, real image. Now there can be different pathways for that because it's stochastic, right? So that way the problem is the training progress is very slow, and it actually generate some arbitrary images from the same seed, and I'm going to show you example. So we want to mitigate this, and we want to incorporate the symmetries, and equivariance is one symmetry, and we'll show that it makes a difference, okay? So equivariance is a general set of transformation like rotation, translation, and scaling, and all this thing. We want to come up with equivalent representation. But transformation I explained to you is general, any transformation. So that's what I just said. So this will enhance the expressibility. We have diffusion model using that. And so here is example. So now what's going to happen, starting from here, there can be different paths to get a noise here, okay? There are different trajectories. So because of that, if you start with the same seed, sometime you will get an image like this, sometime you will get an image like this, sometime you will image like this, because there are different trajectories as stochastic. So that's a problem. Now when we impose the equivalence constraint, you will get these images, and they are all animals, they're more meaningful as compared to these one, and that's the main point here, okay? So we have here image, we transformed it because we want to apply the equivalence for certain transformation, forward process, and then we have a reverse process, and we get an image. Now the problem is that at the end, this image is rotated, but we actually don't want that. We want to, get the, image like this. But we apply this transformation to impose the equivalence, so now we have to deal with that. So which means it's leaking into generative process, generative data. So we have a fix for that. So this unintended transformation permeates into generated images, and that will have the cumulative effect on set of transformation, and it will be a covariant drift. And so therefore distribution of generated data does not accurately represent input data distribution because we have applied the transformation. So what we are going to do, that we'll apply the conditioning. See that you can see that how conditioning is being used in different pieces, and it's very important for diffusion model. Okay, so it's similar to class conditioning as I explained to you. So, but condition now will be transformation. That which transformation we are applying will be that condition, and that will make sure that we can actually deal with this issue. And so we'll apply the conditioning when we train, but when we do the inference, we won't have any condition. So the network will learn that, and that will be important. And that will model seamlessly transition that signify no augmentation. And generated images will remain unaffected by the unintended transformation. Okay? So here is the approach. So this is the simple conventional diffusion model. We take an image x0, x1, x2, we keep adding noise and become like that. And denoising network, which will take the noise and predict the noise, and that's a standard your diffusion model. So this loss we'll call LD, okay? So then, now what we are going to do in addition to that, we'll take an image and rotate it, for example, apply transformation, and then the noise will be also rotated by that amount, and we want to estimate denoising network, estimate this rotated noise with respect to this, and we will call this the loss between this predicted and ground truth, LDT, okay? Transform noise. So then we will want to put this constraint that if we take this noise, apply the transformation, then this should be same as this one. That's equivalence, right? That's what I told you. So then it will be a third loss, equivalent loss. And that's it. So then of course we have the conditioning. So conditioning here is that which transformation applying. Are we applying the rotation and how much degrees? Are we applying the scaling and so on? So there'll be conditioning which we'll put in the denoising network, the new net that I explained to you earlier. So in actually the losses, so this is standard loss. We take the x at time t, and this is conditioning, and then we want to denoising network will estimate the noise, and we want to minimize the ground truth noise, what it predicts, very simple. Then this is the transform noise. So we'll take the image and apply the transformation. Denoising network will predict that, and we know what is the noise, and we minimize this error. And this is the third one, the equivalence. So we want to say that the image applying the transformation and condition T and S, which transformation it is, this should be the same as the taking the image without transformation and the condition T and S, then estimate the noise, then we transform that. That's equivalent. And that's it. So we will use these three losses, we will have some scaling factor, and then it works. So now we will have this conditioning, 512 dimensional embedding S. So we'll have one embedding with no transformation, and we'll have 12 other transformations. So total 13 conditions. And so first we will have the rotation 0 degrees plus 10 minus 10, 90 degrees plus 10 minus 10. Then we'll have horizontal vertical shift by this amount. Then we'll scaling and the spec ratio, and these are all transformation. So we'll add the S condition as the added time steps, and we'll pass the unit. And then during training, we will the no transformation based, and then any of the conditions. Sometime it will be rotation, sometime it will be scaling, and so on. And then inference, we will have no transformation. So we'll get the actual images without transformation. So it works pretty well. So these are the results for C410. This is the without the equivalence, and this is the width. As you see that we can improve. This is the higher the better, and this is lower the better. And these are the images. These are results on Celeb HQ. Again, we do pretty good. And these are the images. And this is for Elson, FID, and this is on the church and bedroom. And these are the images. Then this is ImageNet, which is much, much harder. we can do that. These are images. And so also, because of this constraint, we can actually train quickly. So this one is ours and this is the standard diffusion model. And this is the FID, the quality of images, lower the better. And we did also ablation, that which rotation, what are the transformation make difference. As you see, the rotation actually works the best, but all these scaling, aspect ratio, they also make a difference. And so we did this on the ablation on the pre-trained ImageNet, and here, if you use a stable diffusion and we apply the equivalent transformation, we can make 1.62 improvement FID. And this is a new DIT transformer-based DIT. And again, here we can make a good improvement, okay? So here are different losses, and all the losses actually make improvement. The standard loss, the transform loss, and equivalent loss, and so on, and all that. So in summary, we incorporated symmetry into diffusion models, which enforce equivalence to a general set of transformation. It safeguards the desired data orientation in generated images. We introduced a transformation-based conditioning mechanism. We are using this in training, but inference we don't use transformation, the conditioning, and we demonstrated the consistent gain on multiple data set and compared to standard diffusion model. And we show the results on C410, CELEB, HQ, Elson, and Elson bedroom, and showed improved data efficiency. So high performance gain with limited training data. So that's it. So the last slides. Now, the way I see it, diffusion model is yet another computer vision tool. There's a whole history of computer vision. We have been using different tools over the years. Relaxation labeling with paper from Rosenfeld and Zucker and other guys. Then the graph matching was very popular. Then there's variational calculus, all the MIT work on shape from X. Then there was geometry, Hartley's Zisserman. Geometry was playing very important role. And Markov random field, HMM, MCMC, Monte Carlo, Markov chain, Bayesian networks, graphical models, sparse representation, big of words, SVM. Then there came the deep learning, the CNN, LSTM, GAIN, variational autoencoder, transformers, adapters, and now the diffusion models, okay? Then in parallel, we have large language models and large multimodal models, and so it's continuous. So thank you.
Is there any question inside the audience? Do you have any questions? Or would you like to ask questions? Okay.
Sorry. Maybe, I will repeat. So I'm very interested about the last part of your talk when you introduced this idea of equivariance in diffusion model, because I agree with you that this is very important thing that we'd like to do also in 3D, because we'd like to, do you think this idea that you have developed here can be extended to some other transformations?
Yeah, I think that's a good question. And so as you see here, this was all 2D, so we apply rotation, translation, scale, and aspect ratio. But yeah, you can generalize to the affine, and in 3D also you can do the 3D affine and so on. So these will also make difference, and there are already methods to generate these apply diffusion model to point cloud and 3D LiDAR data and so on. So yeah, it should be fine. Like in other work, we apply the affine. Again, there you have to break the affine in these different parts, because affine is general, which captures the rotation, translation, and so on, and you ultimately have to discretize, and these are the ones we did the 13 discretization, but you can do more than that, yeah.
And maybe last question is about the number of parameters.
Mm-hmm.
I don't see in your presentation if there is some comparison between when you introduce equivalence in diffusion model and without. Do you save maybe the parameters?
Yeah.
Less parameters than?
Yeah, that's a good question. That's what viewers ask us. So yeah, I mean, we have more parameters because of this, but as you see, because of this constraint, as I showed you, it actually does faster convergence. So it is, we have more parameters, but at the same time, we can do actually quicker. Yeah.
Thank you very much.
Yes. Can somebody help? Who's?
Okay.
Là, c'est bon.
Yeah, now it's good.
Yes, thank you very much for the presentation. So my question was about what's the reason that when you do the transformations, it works better? Well, I mean, what's happening in the noise space that make that it works better? That's my question.
Yeah. I think that's a pretty good question, as I showed that this one here, right? That how much rotation, actually the scaling works better, right? So scaling 2.67 and rotation 2.76. So yeah, that's we are still figuring out that what is the why, for example, scaling works better than rotation, right? So maybe in the data set, there are more images which are scaled at different distance and so on, as compared to more rotated, And so also the aspect ratio is another one. The images in these data sets, maybe, they don't have that much, different aspect ratio, the horizontal, vertical. So yeah, I mean, that's what I will say, that, because all this depend on the particular data set, and it's capturing that for the data set, what are the transformation we want to impose to actually improve the results. So.
Thank you very much.
Another
There's
question?
a question here.
Please, is it possible for all of you to present yourself before Lance asking a question, okay? Thank you. Your name, first name, and when you are coming from.
Hello. Thank you. First of all, thank you for the quality of the presentation. So I am Samir Al-Amrani, first year PhD student at the University of Luxembourg. I am working on multimodal machine learning. So I want just to ask, are there some limitations for your work that you have to that you plan to work on in the future?
Yeah, so I think that this area is rich. So what I try to show, diffusion model can be used to solve the different computer vision problems, right? So we demonstrated that it can help to solve the re-ID problem, and I showed that it can help to solve the geolocalization problem. Then I showed also we can use it to apply to action segmentation, and but there are lots of other problems. We can apply the diffusion model to solve this problem, and in terms of improving basic diffusion model. So I showed at the end, so if you introduce this constraint, equivariance constraint, then that helps. But there can be some other, constraints, one has to figure it out how we can improve. Because one criticism with diffusion model is take longer to actually, because you have to have a lot of these steps to converge, to learn this, to how you can make it faster, that's, open direction, and applying diffusion model to 3D data, there's not that much work. And there are all these kind of things, Then the last one is applying to video. So as you saw that OpenAI has this very impressive Sora, video synthesis, and that's where they are applying diffusion model. So the author of the DIT, the diffusion transformer, as you see, the diffusion model mostly is a UNet, like a CNN kind of architecture. But last ICCV last year, there was a nice paper, DIT. The author of that paper is actually author of the source. He showed that for diffusion model, then you can really improve the results. And then he applied that to video, and video are amazing, realistic looking. So I think this is a very rich area. There's lots of interesting problem. One has to discover, nice insights to be able to apply.
You guys say Hajar, but it's the same. Hajra and Hajar is the same. I'm from University of Lille. I'm the PhD student of Professor Daoudi, first year.
Thank you.
Thank you, Mr. Mubarak, for your presentation. Well, you have spoke about person image synthesis, about cloud change in person, and geolocalization, which are great use cases for this model. I just want to know if this model is capable of generating an image from text directly, and if it does, how well does it do compared to existing models such as DALL-E from OpenAI or Midjourney? And thank you.
Yeah, so I think that, OpenAI, DALL-E and all those are the diffusion models, right? So those were earlier, and of course these OpenAI, DALL-E, 2 and so on, they are not open source, but these are these models are better than those were original, a couple of years ago. Things are, improving, and they are standard data set, as I showed you the results comparing all previous method. So, what we have shown here that, open source is stable diffusion. That's the model, which is very powerful, using the latent embedding as compared to original, image model. And we show, for example, last piece that we can improve on the top of latent diffusion, stable diffusion model including if you improve, incorporate the equivariance constraint, and also on the cloth changing re-ID, we use the stable diffusion as the standard model, but we added on top of it the discriminative condition, because as you know, the diffusion model are generative. Now, if you remember, the gain is the adversarial, it's the generative and also the discriminative. It has both parts. So we introduce the discriminative part, and it shows, as I showed you in the ablation, that helps. So we have the state-of-art results, what is published open source, but we don't know what OpenAI does because it's closed.
Nordin Kirzazi, INSEAD School of Engineering. Thank you for this nice presentation. We came across this particular problematic last year when we tried to make some segmentation for the AE disease. We have projects. Lovely. Okay. So we have this kind of retina disease, which is retinopathy, diabetic retinopathy. And we tried last year to remove all blood vessel structure to keep only the residual, hoping that we can find the pathology in this residual. So today we discovered this keyword, diffusion model and denoising. My question is, to what extent we can use these techniques in medical segmentation?
Yeah. I think, as I demonstrated, that diffusion model has been used for segmentation and works pretty well. There's that course here I showed you, this one method, DiffSeg, diffusion model using for segmentation, and it can be used for that. And as I showed you in the video segmentation, which is basically segmentation, right? So we have used diffusion model to do segmentation. So it's a conditional. So see, the thing you have to understand, the diffusion model, unconditional, you take the data set and you take a sample, you keep adding noise, then you sample from noise, denoise, become sample. So it's unconditional. But in order to solve the problem of segmentation, it has to be conditional based on the image or the video. And as I showed you, that we can do that, and they did exactly the same thing in the image segmentation. So yes, it's possible.
Thank you.
Sorry, so that means that we should put all the conferences after the lunch, okay?
Thank you, first of all, for your outstanding presentation. So I think that...
your name, first name, and
yes, sorry, I forgot. So my name is Mubarak Hanan, first year PhD student here in PT. My question is there any related work that aims to apply your approach on 3D dataset? So I think you have worked on the images. So as we all know that there is a huge difference on the two types of the dataset, two-dimensional dataset and the 3D-dimensional dataset. So my question is there any related work that aims to apply your approach on the 3D dataset? Thank you.
Yeah, I think that there's a lot of work because the basic idea is same, right? So you have some data set and it has some distribution, and you sample from the distribution, take one sample, and you noise and denoise and learn the network. So for 3D, it'll be the same thing. Of course, 3D will be that you have point cloud, you know. So there you will also apply the same, exactly same thing. And of course there, you know, you have to have a different, you know, unit architecture, a different point transformer and so on. So there's a lot of work in LiDAR, you know. So it should work exactly the same basic idea. So as I showed, it works for images, it works for video, it will work for LiDAR, point cloud, 3D, like that. And you know, people have even used for the other data, like the tabular data, or even the NLP. You can apply diffusion model to language also. There are some papers doing that. So basic idea is same. You take a sample, you noise and denoise. So you learn the network. Given the noise image, it will give you the denoise image. And you keep doing that, and that's it.
Another question again?